about now?
catastrophic forgetting.
That's
The
fine.
article explains how adaptive resonance overcomes these problems, indeed overcomes 17 problems of deep learning, and outlines a blueprint for achieving autonomous adaptive intelligence. The article is part of a Frontiers in Neurobotics special issue about explainable AI, whose editors wrote, and I quote, "Though deep learning is the main pillar of current AI techniques and is ubiquitous in basic science and real-world applications, it is also flagged by AI researchers for its black box problem. It is easy to fool, and it also cannot explain how it makes a prediction or decision. In other words, deep learning is not trustworthy. No life or death decision, such as a medical or financial decision, can confidently be made based upon a deep learning prediction." Deep learning uses the backpropagation algorithm for learning how to predict output vectors in response to input vectors. Backpropagation was based on perceptron learning principles that Frank Rosenblatt started to introduce in the 1950s. It has a complicated history, which Jürgen Schmidhuber beautifully reviewed in an article from this year. Major contributors include Shinichi Amari, Paul Werbos, and David Parker. Perhaps one would say that it reached its modern form with simulated applications in Paul's 1974 paper before being popularized 12 years later by Rumelhart, Hinton, and Williams. Here's a schematic of a backpropagation circuit reprinted from a survey article by Gail Carpenter of neural network models. In it, information flows feed forward from an input stage to an output stage. Learning is supervised by an external teacher who on each trial defines a target or desired output. The teaching signal is the error or mismatch between the actual and the target outputs. The teaching signal in level F3 of adaptive weights in level F2 have no network pathway whereby to reach from F3 to F2 within the algorithm. So the algorithm uses an artifice called weight transport, which physically lifts the weights from here and moves them there so that they can be used to control learning. Well, this is clearly a non-local operation, as well as being clearly non-biological. Backpropagation learns through slow learning, which means that the adaptive weights change just a little to reduce error on each learning trial. That requires many trials, that is to say, many repetitions of the whole database to learn, possibly hundreds or thousands of trials. This is to be contrasted with fast learning, where adaptive weights zero error signals on each trial, just as we can learn a face that we see just once and remember it for a long time. If backprop tried to use fast learning, it would become wildly unstable. Catastrophic forgetting also occurs in backprop, so that during any learning trial, an unpredictable part of its learned memory can unexpectedly collapse. So deep learning, which is based on backpropagation, is thus neither reliable nor trustworthy. But why is this? One reason is that all inputs are processed by a shared set of learned weights. The algorithm cannot selectively buffer learned weights that is still predictively useful. In particular, there's no attention mechanism. This problem occurs in any learning algorithm whose shared weight updates follow the gradient of the error in response to the current batch of data points while ignoring past batches. There have been multiple efforts to fix backpropagation. One is to selectively slow learning underweights important for learning by optimizing parameters using the Bayes rule, as Kirkpatrick et al. Suggested a few years ago. But that assumes an omniscient observer who can discover and alter the important weights, as well as non-local computations such as the Bayesian computation. The same problem occurs with evolutionary algorithms and diffusion-based neuromodulation and other approaches to try to fix backprop. These efforts to overcome catastrophic forgetting created additional conceptual and computational problems. I view them as adding epicycles to ameliorate a fundamental flaw in the model, which to me is reminiscent of adding epicycles to correct problems in the Ptolemaic model of the solar system. As we all know, the Copernican model that we now accept didn't require epicycles. Perhaps this is why Geoffrey Hinton, who played a key role in developing both backprop and deep learning, said in an Axios interview a few years ago that, quote, he's deeply suspicious of backpropagation. I don't think it's how the brain works. We clearly don't need all the labeled data. My view is throw it all away and start over. I would claim we don't have to start over because these problems were solved in the 1970s and 1980s. In particular, in the first issue of the journal Neural Networks in 1988, I had an article that listed 17 problems of backpropagation that are overcome by adaptive resonance. And here they are. With regard to not needing all the labeled data, I noted in the third item here that self-organized, unsupervised, or supervised learning frees us from needing labels all the time. As to slow learning, I noted that in art you can have fast or slow learning. Indeed, art can learn to classify an entire database using fast learning on a single learning trial, as Gail Carpenter and I showed in the 1980s. Moreover, art overcomes all 17 problems of backpropagation without epicycles. Furthermore, all the core art predictions have been supported by subsequent psychological and neurobiological data. Indeed, art is a principled biological and technological theory, unlike backprop and deep learning, which are just algorithms. Art has explained data from hundreds of experiments, and it's made scores of predictions that have subsequently received experimental support. Well, why has art been so successful? There are a number of reasons, but one of them is that art can be derived from a thought experiment about a universal problem in error correction that I published 40 years ago in Psychological Review. The thought experiment asks the question, how can a coding error be corrected if no individual cell knows that one has occurred? Let me quote from my paper. The importance of this issue becomes clear when we realize that erroneous cues can accidentally be incorporated into a code when our interactions with the environment is simple and will only become evident when our environmental expectations become more demanding. And even if our code perfectly matched a given environment, we would certainly make errors as the environment itself fluctuates. So I was talking about autonomous local learning in a changing world. A purely logical inquiry into error correction is translated at every step of the thought experiment into processes learning autonomously in real time with only locally computed quantities. Moreover, the thought experiment uses familiar environmental facts about how we learn as its hypotheses, and art circuits naturally emerge where these facts are familiar because they're ubiquitous environmental constraints on the evolution of our brains. And since we're living with them all the time, they've become familiar. Because of this universality, art circuits may thus in some form be embodied in all future truly autonomous adaptive intelligent devices, whether biological or artificial. Art has probably, for this reason, already been used in many large-scale engineering and technological applications. In fact, almost immediately after art was introduced, it began being used because it succeeded in benchmark studies against machine learning, backpropagation, statistical methods, genetic algorithms, either getting much better accuracy or much faster training speed, or both. It's also used in applications where other algorithms totally fail, such as the Boeing company's part design, reuse, and inventory compression application. That's just one of many large-scale applications in engineering and technology, some of which can be found on our Tech Lab webpage at bu.edu. The Boeing parts design retrieval system in particular was used to help design the Boeing 777. And to do that, you needed fast learning and stable memory to learn and search a huge and continually growing non-stationary parts inventory. At the time of this application, there are already 16 million 1 million dimensional vectors that were used to describe each of the parts, and you had to be able to quickly search the inventory if you wanted to find a part to use in a new plane, especially if your new design might have a part in the inventory that was similar to it. Finding it and slightly modifying design could save millions of dollars in fabrication costs. Satellite remote sensing is another large-scale application that art was used for very soon. And Gail Carpenter and her colleagues took the lead here. For example, using a very small number of pixels of ground truth of 17 vegetation classes, they used art to automatically complete these maps using remote sensing data. Art did it in a day, rapidly and automatically. It gave a confidence map for each pixel, and the pixels were 30 meters in scale, which was small enough to see roads. This contrasted with an AI expert system, which took a whole year to do it, and it had to derive ad hoc rules from experts. You had to correct upwards of 250,000 site labels, and even so, the pixel size was an order of magnitude larger. Gail went on with her colleagues to study information fusion in remote sensing. Let's say you have multiple observers. Each of them may be using different labels. Their labels may also be incomplete or missing or even incorrect. And the task was to derive consistent knowledge from potentially inconsistent data to automatically learn and stably store one-to-many mappings. And along the way, Gail and a colleague showed how to self-organize a hierarchy of cognitive rules, including confidence measures between these different levels of the hierarchy. There's been continual work on art. Some more recent work was summarized in a special issue of Neural Networks just in December 2019 that was edited by Donald Wunsch, who started the special issue with a general overview of neural network models that I and my colleagues developed, and then went on in a long and detailed article with several collaborators to provide a survey of adaptive resonance theory neural network models for engineering applications to the present time. So backpropagation and deep learning are a feed-forward adaptive filter, but art is more than that. In fact, art is an explainable, self-organizing production system in a non-stationary world. What do these words mean? Art self-organizing because it can autonomously carry out arbitrary combinations of unsupervised or supervised learning trials with the world as its only teacher. It's a production system because it uses hypothesis testing to discover and learn rules by a top-down matching process that focuses attention on critical feature patterns. These are the patterns that predict behavioral success while suppressing irrelevant features. Art's explainable using both its activities or short-term memory, STM traces, and its adaptive weights or long-term memory, LTM traces. Activation dynamics, learning dynamics. Observing the STM traces in a critical feature pattern explain what recognition categories will learn to code and what features predict goal-oriented actions. In particular, the long-term memory traces in the fuzzy art map algorithm translate into explicit fuzzy if-then rules that code what combinations of critical features in what numerical ranges effectively control predictions, thereby illustrating one of many examples where neural networks can learn rule-based behaviors. Art includes a bottom-up adaptive filter or feed-forward neural network, as I've observed already, but that's supplemented by top-down learned expectations and two types of recurrent inhibitory feedback interactions that help to choose the recognition categories and the critical features. Notably, top-down expectations use what Gail Carpenter and I call the art matching rule to learn how to focus attention on critical features that control predictive success. The art matching rule is another way of talking computationally about the process of object attention, how we pay attention to salient objects in the world. And we show how it stabilizes learning and thereby avoids catastrophic forgetting. Remarkably, and this has been supported by many data, the art matching rule can be realized by a top-down modulatory on-center off-surround network. Well, what does this mean? Well, let's say we have bottom-up inputs from external features to feature selective cells that get stored in short-term memory. Let's say we activate a recognition category, which has previously been learned, and it tries to read out its learned excitatory prototype. Well, it can't fully do so because it also reads out an inhibitory off-surround that's broader than the prototype. And so this is approximately one excitatory against one inhibitory. It can only give you a modulatory on-center. But if you have both bottom-up inputs and the top-down expectation simultaneously active, then within the bounds of the prototype, if you also have a bottom-up feature, you have two excitatory against one inhibitory, and those features can be selected, gain amplified, and synchronized to start focusing attention on this critical feature pattern, while outlier features, the ones that aren't within the prototype, only have one excitation against one inhibition, are suppressed. And in 1999, I was able to begin to understand how lamina cortical circuits carry out object attention. In particular, layer 6 of a higher cortical area can activate layer 6 of a lower cortical area, either directly or via layer 5. And then it can fold up to layer 4 to modulate an on-center and to inhibit an off-surround. So attention acts via a top-down modulatory on-center off-surround network via folded feedback within lamina neocortex. And this is one example of the paradigm of laminar computing that I introduced, which asks why are all neocortical circuits organized in layers, and how do laminar circuits give rise to all kinds of biological intelligence. Adaptive resonance enters the story because attended feature clusters reactivate their bottom-up pathways. Activated categories reactivate their top-down pathways, closing an excitatory feedback loop between features and categories, giving rise to a feature category resonance that synchronizes, amplifies, and prolongs system response between the attended critical features and the category to which they are bound. And it's this resonance that triggers fast learning in the bottom-up and top-down adaptive weights, which is why I have called the theory adaptive resonance theory. Moreover, I've done a lot of work since then showing that all conscious states are resonant states, and these feature category resonances are one example of that, one that supports conscious recognition of visual objects and scenes. There's a lot of data support for art predictions. It's well known that attention does have an on-center off-surround circuit behind it, and that attention can facilitate matched bottom-up signals, many other data as well. So now we can say more about why art is explainable or trustworthy. In short-term memory, it's because the critical feature patterns determine the attentional focus that controls information processing, and you can just read off what those features are. In long-term memory, again, it's the critical feature patterns that determine the adaptive weights learned by the bottom-up adaptive filter and the top-down learned expectation. So you know also what these weights are encoding. Art's reliable and avoids catastrophic forgetting because outlier features that are not in the critical feature pattern are suppressed, so that only the predictive features are processed and coded. Art's a production system because it carries out a kind of hypothesis testing, and this is nicely illustrated in the simplest art model called Part1 that Gail Carpenter and I published in 1987. Part1 has an attentional system that does all the category learning and the expectation learning and the paying of attention, that interacts with an orienting system, which is activated when there are big enough matches in the attentional system, and thereby drives a reset and search for novel or better matching categories. Here's a schematic of the art hypothesis testing and learning cycle. So let's say you have a bottom-up feature pattern coming in. There may be many, many active bottom-up features, but I'll draw just one arrow here for simplicity. But that vector of input features can activate a distributed pattern of feature detector cells. Some may be very active, some not so active, some not active at all. And as this is happening, each of these active pathways is trying to turn on the orienting system. So there might be quite a few inputs converging here. But as the features are activated, each of them tries to inhibit the orienting system. And there are as many features as there are inputs. So this excitation, inhibition, a balance, keeping the orienting system quiet as the feature pattern goes through the adaptive filter and chooses a category. That category reads out a learned top-down expectation that obeys the art matching rule, which can suppress some mismatched features, thereby reducing the amount of inhibition on the orienting system and raising the question, when you have too little inhibition and too much excitation, how big a mismatch will activate the orienting system and cause reset? And that ratio is determined by what's called vigilance, which I'll say more about soon. But if you don't have enough inhibition, then the orienting system gets activated. It equally activates all the cells in the category layer because it doesn't know which cell may be active or not. So it causes a novelty sensitive, non-specific burst of arousal. Novel events are arousing, thereby selectively shutting off the active category, eliminating its top-down expectation, and unmasking the original feature pattern, which can again go through the adaptive filter. However, now, this previously disconfirmed category remains off, and the category level is renormalized, so it responds to the same input pattern with a new category, and you go through this cycle of resonance and reset until you get a good enough match to either learn a new category or select a previously learned category. And it's a theorem that as categories are learned through this matching process, search automatically disengages, leading to direct access without search to the globally best matching category. Explaining, for example, how we can quickly recognize familiar objects like your mother's face, even if as we get older, we store enormous numbers of additional memories. So you don't have to search your whole repertoire. When you see mom, you get direct access and quickly say, hi, mom. There's a lot of support for the hypothesis testing cycle. One source of support is from event-related potentials, also called human scalp potentials, which shows correlated sequences of 3 different evoked potentials during oddball learning tasks, an experiment that John Paul Bankay and I reported in the 80s, where you'll get a P120 for a mismatch, an N200 for the arousal activated by the orienting system, and a P300 for the short-term memory reset of the category layer, thereby supporting the processing stages of the search cycle. There was also physiological data from infratemporal cortex where categories are learned early on from the lab of Bob Desimone, who showed an active matching process that's reset between trials during this kind of event. There's also classical data about hippocampal mismatch dynamics. It's known that novelty potentials subside as learning proceeds from numerous experiments. This is as the orienting system is disengaged. And there's more recent data using multiple electrode studies from the lab of Earl Miller from prefrontal cortex and simultaneous recordings in hippocampus. And they show there's rapid object associative learning may occur in prefrontal cortex, which is a projection of infratemporal cortex, one of the stages of category learning, while the hippocampus may guide neocortical plasticity by signaling success or failure. Well, this is just what happens when the attentional system interacts with the orienting system. There's also complementary computing in art. In particular, the attentional and orienting system laws are complementary as manifested by the fact that 2 event-related potentials are complementary, processing negativity and N200. Processing negativity is activated when there's a top-down match in the attentional system. The N200, as I just noted, is activated when there's a mismatch that activates the orienting system. And you can just look across these 4 rows and see that these 2 kinds of ERP potentials are manifestly complementary as illustrative of the complementarity of the attentional and orienting systems. So this leads us to discuss another paradigm introduced, which I call complementary computing, that asks, what is the nature of brain specialization? Complementary computing introduces new principles of uncertainty and complementarity that clarify why there are multiple parallel processing streams with multiple processing stages in our brains. And a beautiful example of that is this famous image of the macro circuit of the visual system from David Van Essen and his colleagues, where you can see these multiple parallel processing streams and the multiple stages needed to achieve what I call hierarchical resolution of uncertainty. But what are complementary properties? They're analogies, like a key fits into a lock, or puzzle pieces fitting together. In words, computing one set of properties at a processing stage prevents that stage from computing a complementary set of properties. These complementary parallel processing streams are balanced against one another. It's a very yin-yang kind of situation, and interactions between the streams overcome their complementary weaknesses. In fact, there are many complementary processes that are known in the brain that have been modeled. Here is just 5 of them. There are many more. So this is a basic principle of brain organization. So in summary so far, backpropagation and deep learning do not have short-term memory activation patterns, including critical feature patterns, so they can't pay attention. Indeed, they don't have any fast information processing, nor do they have long-term memory top-down learned expectations, so they can't carry out hypothesis testing using interactions, short-term and long-term memory traces. Indeed, there's no neural architecture, there's just an algorithm, in really great contrast with complementary computing, which discusses the global organization of our brains. From the very start, it was shown how easy it is to get catastrophic forgetting, and Carpenter and I showed it in art when we would shut down the art matching rule. Then we demonstrated you could get catastrophic forgetting if you had just 4 input vectors, A, B, C, D, presented in the order A, B, C, A, D, A, B, C, A, D, and so on, if they obeyed very simple subset relationships. And here's a computer simulation of that. Here you don't have the arc matching rule. Here's A, B, C, A, D, A, B, C, A, D. And you see A is coded by category 1 here, by category 2 here, by category 1 here, 2 here. It never settles down. But as soon as you impose the arc matching rule, learning is complete by the second trial. And after that point, you get direct access to the globally best matching category. Well, let's say a little more about vigilance. Vigilance determines what features are learned in the critical feature pattern. It clarifies how our brains learn concrete knowledge for some tasks and abstract knowledge for others. So in particular, high vigilance leads to learning of narrow, concrete categories, like a category that fires selectively to a frontal view of your mother's face. Low vigilance leads to learning of broad and abstract categories, like everyone has a face. It should be emphasized that critical feature patterns are explainable at every level of vigilance. It's known from physiological experiments by Desimone again, that there's vigilance control in the infratemporal cortex, which they showed by studying easy versus difficult discriminations in monkeys. And in the difficult condition, which you'd assume would give you high vigilance, as expected, you had enhancement of the responses and sharpened selectivity to the attended stimuli. How is vigilance computed? Well, let's say you have input vector. It instates a vector of activities it feature detectors at the same time as it tries to activate the learning system, but it does so multiplied by a parameter rho, which is a sensitivity or gain parameter. That's vigilance. And as these features get in state, they try to shut off the orienting system. And if the excitation is less than the inhibition, the orienting system stays quiet, so the system can resonate and learn. But if inhibition isn't strong enough, the orienting system gets activated, you get reset and search for new categories. This is a very simple computation because you have an orienting system that's complementary